My name is Eve McDonald and I'm the EMESRT coordinator. I'm just going to cover the agenda for today's webinar and then we'll get into it. So I'll just cover some housekeeping very briefly. Part 1 will be presented by Tony Egan, our EMESRT Glencore rep, and Tony will provide us with a welcome and an introduction. Part 2 is the project presentation, and that'll be delivered by Dasan Gunasingi, Mining 3 research engineer. Part 3 will be the question and answer session, and Tony Egan is going to facilitate that. Part 4 is the conclusion and next steps, and once again, Tony has put his hand up to do that as well. Okay, Tony, if you wouldn't mind, please providing us with a welcome and introduction.
Thank you, Eve. In terms of this project, its genesis was back in 2013. Ian Curran, who was with Rio at the time, he's now with BHP, walked in the door of the EMESRT advisory group and said, we've got a burning platform around this vehicle collision stuff. And at the time, what ensued from there was a body of work that occurred and a definition of what was the real problem, because originally we talked about collisions and proximity detection, everything, they're all controls. The real issue was vehicle interaction. That's the problem. And it's got many facets to it. During the course of that work, there was several things identified that really needed the industry to come together if we were going to move forward at any pace. One of those things was that the fact that there was no interface protocol between that was available between proximity systems and OEM equipment. Now, if you went to marine or airlines, trains, those sorts of things, even automobiles, there was standards in terms of those interfaces. And so that's one area that we operated in, and the ISO standard hopefully will be published this month, ISO 21815, to do with that interface protocol. The other major piece of work is the one that we're going to talk to today, which was there was no common testing methodology. It was everyone to their own. And that becomes an issue, particularly as a buyer of something. You know, you go out and buy a car, say in Australia, and there's an ANCAP level of 5, and you can go and read what that looks like. It's an analogy, I suppose. So what we set out to do was to say, can we actually bring the industry together? And off the back of the group that we formed to look at the interface protocol, which brought OEMs and third parties and other technical people together, you know, I think in the end was 100 and something. There's over 150 people involved in that group now. We leveraged off that group to also get involved with this exercise. We got funding from ACARP, Australian Coal Research Projects, for what's now been 3 phases of this project. There was an initial phase with a young gentleman named Joel Koch, who led that in the early days, phases 1 and 2. And it's now gone to this phase 3, which Dasan and his team have been involved in for the last few years. So it's been over a period of 5 or 6 years. So it's not something that was dreamt up overnight. It's been quite an arduous set of work. So that's the background to it. The real premise of today was that the industry group has been involved in workshops along the way. We've had several in Brisbane over the years. We haven't been back together for a while. And today was an opportunity to feed back the final report, which is being published by ACARP as the first formal step, with a view that the ISO 21815 committee has asked us to bring forward a submission around a testing methodology and whether that might be appropriate to go into one of the standards in some form. And that's another arduous process in itself. We can tell you that from the interface protocol process we've been through. So looking for your input today, and be as blank and as open as you like. We really want some robust feedback about where this is going, because at the end of the day, we really do need some commonality here if we want to accelerate this process with all of this technology coming into the industry. So over to you, Dasan.
Thanks, Tony. Let me just quickly share my screen. Can everyone see that okay? Eve, I suppose you could speak to that?
Yes, thank you, Dasan.
Yes, perfect. All right, thank you for that introduction, Tony, and welcome everyone to this morning's session. Really grateful to actually be able to present the bulk of the work that we've done for the last year and a bit. So I'll be speaking on behalf of our team, discussing essentially the outcomes of our field work and the guideline development that we've done in terms of the final report. Before I really begin, I do want to stress that this is a big bulk of work, and I really want to put forth some acknowledgements to a lot of people, and without whom this project would not have been the success it was. So ACARP, and specifically industry monitors Tony, Matthew, Mark, Campbell, and Ian. Without your feedback and input throughout the project, we wouldn't have got to the stage. Also like to thank EMESRT, the advisory group, both the current and the previous members. In terms of our external collaboration, I'd like to thank Dr. Herman Hermersma from the University of Pretoria, Professor Robin Burgess-Limerick from the University of Queensland, and Dr. Mark Dunn from CSIRO for their input and involvement in the previous and current phases of the work. I'd also like to stress and thank the 3 anonymous PDS suppliers for the donation of their systems, as well as the involvement of their site engineers for the installation and calibration, without whom we would not have had the field test work conducted. From our end of things, I'd like to really thank our CEO, Professor Paul Lever, Susan, who's our COO and project leader, Dr. Isaac Dizak-Patav, who's a work area leader here, as well as Ian, Chris, Joel from previous work, and Eve as well for your involvement in this project, and thank you so much. For anyone else who we may not have covered in this list here. So the main agenda of this morning's presentation is just to talk about the overall project objectives, and this is also talking about really the methodology objectives as a whole as well, and some of the achievements. Then I'll focus on the external collaboration, specifically looking at the user interface and the PDS sensor toolkit outcomes. Then I'll dive into the bulk of the work, which is our capability assessment methodology. And this involves discussing the test plan, its development, including the data acquisition system that was put in place to capture some of the information, as well as examples from the data evaluation process and some learnings that we've found. And then finally, I'll conclude by discussing the overall outcomes and some of the recommendations regarding any remaining gaps that exist. The project objectives can essentially be put into 4 buckets, and 2 of those components rely on providing the guidance and the knowledge towards really the development of the user interface in terms of its functionality and some testing recommendations, as well as looking at sensor considerations that exist in the industry to date. And this covers some of the common sensor technologies, as well as discussing some important facts regarding sensor fusion and providing that information and knowledge to the industry. The second component is really looking at the development of a unified test methodology, as Tony mentioned previously. And this involves looking at some of the key factors that we would like to test that are relevant to PDS, specifically looking and targeting level 7. And just for those in the audience, level 7 really discusses the operator awareness or the situational awareness. Level 8 and beyond, level 8 specifically looks more at advisory controls. So some elements of level 8 have been looked at in this phase of work. But level 9 and a majority of level 8 have not been covered to date, as this involves more intervention controls with the actual machine itself, which is something we didn't have on site to look at and test properly. Part of that development process also involved an independent review to categorize some of the more prevalent scenarios that actually show alignment to the PR5A scenarios. And this was largely done to understand what sort of testing can be done practically, and to understand how safely and rigorously we can do that in terms of scientific rigor. Now, in terms of the methodology objectives, this can also be divided into 4 buckets, essentially, and these 4 buckets represent some of the main achievements that we would like to achieve and have achieved. So the first point is trying to make sure that this methodology is realistic. So this is essentially discussing the ability of this methodology to involve representative vehicles. So in our particular case, we used a haul truck, a CAT 777B that was available to us on site, as well as a light vehicle, and also the inclusion of those prevalent scenarios that show alignment to the previously determined PR5A scenarios for open cut mines. The second point is we wanted to achieve technical and physical achievability of the methodology. And this is twofold. This is looking at whether the test methodology can be essentially reproduced at a different site, as well as whether the test methodology can be conducted under different PDS systems as well. And this is important because the design elements can change, and we wanted to see whether the capability could still be reported in a similar manner to understand the baseline capability of that system. The third point is efficiency, looking at really how long and how effectively how long it takes for the test process to be conducted. And we found that it took approximately 9 hours for all the tests that we developed, which I'll be discussing a bit more in detail later, which is looking at around 2 days, taking into account repeat tests and breaks, which is a good starting point for at least baseline capability testing. And finally, we wanted to ensure scientific rigor. And this is really involving the methodology's ability to include repeatability of some of the tests and some randomization to get statistical significant findings. So as I mentioned previously, the external collaboration focused primarily on giving a lot of guidance to the industry. And the first point of call is the user interface design. So this was formed from a collection of findings from previous work that was conducted by Professor Robert Burgess Limerick, and includes some of the do's and don'ts of UI design, as well as recommendations for improving UI design as well. Importantly, it actually includes some operator adaptation and some feedback from operators themselves in terms of suggested changes for a better change management process, and even more of the actual change management regarding evolution of the system into the future once it's implemented. It also includes some gaps and some areas of future research specifically targeting the user interface design. In terms of the PDS sensor toolkit, so this was a collection of findings from Herman Emasma from University of Pretoria. In collaboration with Mining3, we developed and put forth or deployed an online toolkit that is now available to the industry. And this involves essentially sensor-based information that is prevalent to PDS in this current point in time. And this involves the working principles of those systems, of those sensors, discussions really regarding the application of those sensors to PDS, some of the advantages and limitations of each of those individual sensors, as well as discussing the collaboration of those sensors together in a fusion methodology as well. So as I discussed earlier, this is now the main bulk of the work. And part of that process actually involved identifying some of the prevalent scenarios to ensure that the field tests were conducted in a realistic and safe manner. So out of the main component of scenarios that we evaluated based on the EMESRT PR5A, these were all bucketed into 6 major scenarios, as you can see in the table on screen. So we've got intersection-based cases, we've got work area conflicts, we have tailgate or direct encounters, we have something called a static road hazard, effectively a dynamic object encountering a static object, which is either on the side of the road or another vehicle. And loss of control, which is actually divided into 2 subcategories, this being either an interaction with a void or an interaction that occurs on an inclined surface. Now, as you can see in that first row, this aligns a lot of the open-cut EMESRT PR5A scenarios as we would like to achieve. I've also included a few extra different guidelines that actually have similar scenarios, and you can see their alignment as well to these major prevalent scenarios. So this essentially gives us an understanding of which types of scenarios we can now choreograph towards a test procedure. So in terms of the test plan, part of that process, other than identifying the prevalent scenarios, is also now identifying some of the key factors that would imply change in the PDS system or unit itself. So it looks at the distance between 2 objects, the speed as well of those 2 objects, the object size itself, whether it be a Cat 777 or a light vehicle, as well as the trajectory, and this being looking at specifically at either a straight line trajectory or a curving, a bit slightly more complex trajectory as well. From the development of the test plan, we had 3 major test types. So the first one is a detection shape or zone classification test, as shown on the right image. This effectively had the haul truck static at the center, with our light vehicle object dynamic in a straight line at different orientations about that haul truck. And what this does is once we've tracked and quantified the results, it essentially shows a shape of the detection, the alarms that occur for that particular system around the object of interest, in this case, the haul truck. And this allows comparison essentially with what the specification says and any issues that arise out of that process. The second test is a more rigorous scientific test, which is a design of experiments, and this tests those key factors that I discussed earlier. And this is shown on the right in a very high-level way. So as you can see, the haul truck is shown as the example here in the middle, where we have our dynamic object, this being the light vehicle, that actually enters either a inner circle, a shorter diameter circle radius around the whole truck or a larger diameter circle around the whole truck. And this tests that distance factor. We also test going around the whole truck as well as traversing straight in a perpendicular fashion, which tests the straight line or curving dynamic cases. We also test different speeds, and the object size is tested by switching out which object is in the center and which object is dynamic. So in some cases, we'll have the light vehicle in the center and the whole truck going about the trajectories as shown. The final test is essentially a choreographed version of those prevalent scenarios that I discussed earlier. The idea here is that any areas of interest that were not identified in the previous tests, we can now specifically choreograph and understand the outcome of or the capability of the PDS. And shown here is an example of one of those key tests. And this is where the whole truck is directly driven at either a light vehicle or a mannequin object, which represents a pedestrian. Now, a main bulk of the development of this test plan really involved ensuring that every test was conducted in a safe manner and choreographed in a safe manner. So taking this image, for example, we ensured that there were stopping distances and everything was unmanned and everyone was out of the exclusion zone, and this is prevalent to ensure that safety remains prudent throughout all the testing. Another example really is looking back at that test 2, the design of experiments. Specifically, when we wanted to test object size, we had to have the whole truck and the light vehicle swapping that position. And we ensured that the test is developed such that we can switch those out without any interaction between the two occurring. So the data acquisition system played a heavy role in ensuring that we captured time-synchronized data, as well as ensuring that the system was developed in an open source manner so that it can be reproducible by the industry. So this involved the robot operating system, also known as ROS, which allows us to essentially run the same operating system on multiple computers and have all of those computers time synchronized to a single server and have that data essentially recorded all at once and then post-analyzed for data analysis. So the bottom table or the graph there actually represents the high-level overview of our data acquisition system. As you can see, there are 4 major computers used on site. So we have the control center, which runs effectively the recording cycle and the overall control of the system. We have 2 main computers situated on the actual dynamic objects themselves, this being the CAT 777 and the light vehicle. We also had an external computer located in the test arena, known as bystander, to capture any visual information that might be important to the data analysis. On top of those 4 computers, we also had additional cameras to capture the test environment, as well as a drone to capture overhead views of the test environment as well. So here's a quick snapshot, really, of the data acquisition in motion. So on the right, this is what we essentially get with the post-analysis. We can see some of the LiDAR equipment that we had on the light vehicle capturing a pedestrian object, and this allowed us to capture that distance and measure that distance in a ground truth fashion to ensure that the alert type matched the corresponding encounter. On the left is actually a high-level view of the timeline and the recorded data that's captured from all the 4 computers, which required analysis to understand the capability of that system. You can actually see there's a snapshot and a modeling of the overall test pad with the whole truck and the light vehicle represented as models, with LiDAR data as well as vision, stereo vision data captured. And most importantly, cameras located inside the cabins captured time-synchronized views of the actual interfaces themselves that give feedback to the operator. So this data acquisition system, it's essentially ensured the capture of the relative position and the orientation between the local object and the remote object in the tests that we conducted. It also captured that relative speed in order to understand each of the key baseline factors. And as I mentioned previously, it very importantly captured the visual as well as the audio capture of each of the PDS interfaces on both of the light vehicle and the whole truck PDS systems. And this allows us to understand if there's any differences between the 2 implementations based on the type of object it's implemented on, as well as any nuisance alarming that may occur. The evaluation process itself also involved the development of some scripts in order to automate a lot of the process itself, but this still largely required a lot of manual analysis in order to view what the PDS system was displaying to the user and effectively categorize that with what the spatial data was showing from the capture of GPS positions and LiDAR data. Now, in terms of the actual categorization and determining capability, this was done through an alert type designation. This is done in a very general way to understand whether an alert type 1 represents either the actual detection or the conveyance of object awareness to the operator. This is a level 7 detection. Anything above that essentially shows additional levels of intelligence and alert types that may be prevalent to that particular system. So alert type 2 and onwards can be either an audible tone or a visual indicator, but this shows some differences between systems that can be used for comparative sakes. So now I'll go through very briefly some examples from the data analysis that we conducted from each of the 3 major tests. So shown here is an example from test 1. As you can see, if we focus in on this first row, this represents the light vehicle's PDS interface perspective. As you can see, the light vehicle in this context is driving dynamically to the haul truck, which represents the shape test that was discussed earlier around the haul truck object. And the left image corresponds to a low speed test versus the mid speed test in the middle and the higher speed light vehicle test on the right. So from this information, we can see that this system certainly implies cell level 7 detection, as well as some higher level alerts to the operator. And you can actually see that high level alert changes with respect to speed, demonstrating that as a factor. Now, looking at the exact same scenario from the haul truck's perspective, we see an interesting difference from this particular supplier. Again, the level 7 detection is displayed to the operator on the haul truck. But again, the number of alerts issued to the haul truck driver is actually less in terms of the light vehicle operator's PDS on the same system. So this is an important understanding to relay from these tests that we conducted. So now this is an example from test 2. As I mentioned, test 2 is a design of experiments test, and it involves essentially a lot of different interactions and different configurations of those baseline factors. And this is just one specific case of that. And if we focus in on this first row, this essentially shows the light vehicle is central in that circular form, and we have the haul truck translating about the smallest radius circle around the light vehicle and exiting to the left. On the left-hand side, if we split this image in two, represents the haul truck's perspective, and on the right we see the light vehicle's perspective of this particular system. And this is supplied to, once again, for reference. And now, as expected, the haul truck's detection doesn't show anything beyond an alert type 2, so there's only 2 alerts really represented to the operator in this case. The next remaining rows effectively show a repeat of this particular case. So this is the repetition that was conducted in a randomized fashion. Now, what's interesting here is that this particular system demonstrates a purely proximity-based implementation. As you can see on the right, the haul truck is dynamic and the light vehicle's alert changes with respect to how close that haul truck gets as it comes into the circular radius around the light vehicle and then exits the circular trajectory. Now, comparing this to supply 3's data of the exact same scenario shows how different some of the systems can be implemented, even if these 2 suppliers essentially have the same infrastructure in terms of their sensor. So as you can see, once again, the left-hand side is the haul truck, and this shows some, it doesn't detect as much in terms of the dynamic object. But something interesting to note when you look at C and D is that this particular system actually prioritizes alerting when it interacts in a certain way. And this particular case is when it traverses in front of the light vehicle, as you can see with the orange detection on graph C and the orange and yellow detections in graph E. On the right, in terms of the light vehicle's trigger, we can also see more of a dynamic interaction in the front view of the light vehicle, with some alerting occurring as it traverses around. And this shows some variance as well when we compare A, B to graph C and D, and even comparing it to E and F, which is important to understand for that particular system. Now we move on to the test 3 sections, and these are those choreographed cases of the prevalent scenarios. This first one is a very interesting one. This essentially had our haul truck static at the center point of our test pad, and we brought the light vehicle as close as possible to the haul truck at 3 major points of interest, either the front of the haul truck, the side of it, or the rear of the haul truck. And we also tested this with the pedestrian object, the mannequin, at the same orientations. So focusing on graphs A and B, this is supply 2's outcome from this test. And the point of this test is to have the system completely boot up from a cold start and understand how long it takes for that system to detect that object that is quite close to the local object. So the left-hand side shows the detection from interacting a haul truck with a light vehicle up close. And on the right, we see the detection of the pedestrian object with respect to the haul truck for that particular system. Of interest is the left-hand side for specifically supply 2. We see that there's some faster detection on the light vehicle, specifically at the front, with the more consistent detection of the light vehicle on the side and the rear. Interestingly, though, the pedestrian object, on the other hand, is actually detected much faster and more consistently around the haul truck. And this could be attributed to using different technology, different sensor technology for that particular case, but it also boils down to the final implementation of how that's conveyed to the operator. Now, looking at supply 3, which is the bottom graph now, of the exact same case, we see a more consistent outcome, regardless of whether it's a light vehicle or a pedestrian. Interestingly, with this system, you can see there's a longer bar. So this bar represents first an audible alert that gets issued at approximately 65 seconds, consistently across the board. But then a visual position is actually identified a little bit later, roughly 20 seconds later, as indicated from these results. So this is an important understanding of that system that can get conveyed to the final user. Another example from our choreographed scenarios is showing a dynamic passing case, which is very prevalent in most mine sites, if not every mine site. So we have our dynamic case with the haul truck and the light vehicle traversing itself either at a low speed on the left or at a high speed on the right. And this is with supply 2. So this is interesting. We can see that there is some differences in having speed as a factor, as we identified previously in our first test. And I want to point out that both these systems use a GNS-based or GPS-based system, and it wasn't expected to have speed being a factor, yet its integration and final implementation is what makes that key difference to the user. In contrast, we look at supply 3's outcome from the same case in terms of graphs A and B. Now, there's some additional information in graph C and D in below showing additional variance tests. So this has either the haul truck traversing at a low speed and a light vehicle traversing at a high speed, and vice versa, to understand if there's any differences there. Interestingly enough, if I go back to supply 2, you can see that this system essentially alerts throughout the entire encounter and even beyond the encounter. This is how it's designed. On the other hand, with this particular system, you can see that past the point of interaction, it goes back to an alert type 1, which is just a visual or a basic detection of that system. So this can infer some important aspects in terms of deciding what type of system to go forward with for that user and any areas of improvement that could occur as well. So now onto the final section in terms of overall recommendations and advantages. So I go back to those main 4 buckets that we wanted to achieve in terms of our objectives for the methodology. So first and foremost, we wanted to ensure that it was realistic, and we managed to do that at least in a very baseline way, and by using a haul truck that was available to us on site and testing actual PDS units that were donated to us to understand their baseline capability, as well as understand the outcome of the methodology itself. We also wanted to ensure that this was technically and physically achievable at different sites. This was done by essentially involving the team at University of Pretoria to run through a first iteration of our test plan and get some learnings from that to enforce the final test plan that was conducted on site here to ensure that we managed to deploy this and obtain the same amount of information at any different site. We were also able to conduct this test with the donation of different PDS units as well, which is a good outcome for this project. Finally, this test was quite efficient in terms of the actual testing. As mentioned previously, this took around 9 hours of test time and an approximate 2-day window for testing in total. That's not including the actual setup of the data acquisition system or the data evaluation process. And finally, we wanted to ensure scientific rigor, and this involved the design of experiments cases with repeated tests and randomization to understand that variance in that test and infer some statistical significance from the results. Now, in terms of the limitations, as I mentioned, we did define 6 prevalent scenarios. However, capturing all 6 of those choreographed scenarios was a challenge, largely due to safety concerns, specifically that intersection case where we would have to have 2 manned vehicles intersecting in a cross-like fashion, which we avoided for safety concerns and safety reasons. Site practicality also ensured some testing, such as the void cases where we did not have that available to us, or an inclined surface as well, for that matter. So there's some areas that could be bridged by taking this test plan to a proving ground to understand the capability on these particular choreographed scenarios. The data analysis, while conducted in somewhat of an automated fashion with some scripting, still involved a largely manual process, because it involved looking at the outcome of the PDS interface captured either through audio or by visual means, and then categorizing that to an alert type that corresponds to spatial information of those objects. So this could be potentially outsourced to a third party to make this a bit more efficient, and further development on the automation of some of these scripts, as well as even automation of visually capturing some of that information could be done, but this is really out of scope and more into future work. Finally, the main objective at this point in time was looking at that level 7, that operator awareness capability of these systems, and some elements of level 8. So looking at that alert types and what sort of intelligence occurs. But a large component of level 8 and even level 9, which is a full integration, was not covered in this scope. And this presents a significant challenge going into the future, as it essentially involves a validation not only of the PDS itself, but also the full mechanical system that involves the collision avoidance system, and as well as the vehicle actually responding to the decisions that PDS has made. So this may potentially require simulation or a practical environment such as a proving ground to quantify the capability. And it may not even involve unmanned vehicles. It could involve fully autonomous setup vehicles as well. And this is very important when we consider that the intelligence layer can actually be designed in different ways, which is actually evident from some of the examples that I presented this morning, which show that even if the same sensing suite is used, some of the outcomes could be different and present added complexity in the validation of some of these completed systems. Overall, we managed to achieve vehicle-to-vehicle and some vehicle-to-pedestrian encounters as displayed previously, but some of the more complex scenarios, such as multiple vehicle interactions and more dynamic speed scenarios and trajectories, were not attempted due to the complex nature of these, as well as the unavailability of some of the vehicles on site, as well as the site practicality itself. So the image on the left you're seeing now is a snapshot of the gap analysis that was performed at the very beginning of phase 3 in the first webinar that was in September of 2019, I believe. So at this stage, and this is from the Pacific Mining 3, we can see that largely the experimental design and a field test executable plan was developed for the object detection in terms of inline and level 8 and 9 for inline and parallel cases. However, the actual hard test, the field test instrumentation and hardware was not developed at this point, so the methodology was unable to be validated up to this point in time. On top of that, the actual inclusion of more complex cases such as intersections and curves was not considered in this particular methodology at this point in time. I'm happy to say that a lot of this area has been developed, as we see in a snapshot of today's outcomes. So that initial row essentially shows that we have level 7 detection with inline and parallel cases that were tested on site, with some field test instrumentation developed for really all types of tests going forward, and some validation considered as well from the methodology's point of view. Now, there's some areas that have been highlighted as developed but limited, and this is largely due to not having encountered a majority of that level 8 and level 9 component, which requires potentially simulation or practical proving ground testing. It's also considered a significant gap at this point going forward due to that safety component. I'd also like to point out that while we are able to simulate some complex cases such as curving trajectories, there are still more complex and more dynamic cases out there, especially when we include multi-vehicle interactions. So this also presents a gap that needs to be discussed and looked into for future work. So that concludes my presentation for this morning. Thank you everyone for listening. I'll now hand it over back to Tony to conclude this morning's webinar.
So thank you, Dustin. I think everyone on the call, if you had an invite, you should have received a copy of the ACARP report as prepared by the team, and also some other an access to the sensor website. So they were sent out a couple of days ago. Hopefully you've had a chance to look at those. At this point, I'm got a problem with my browser and I can't see the chat line, so I'm going to get Eve to run the chat process. But Dustin, I'm just going to kick off with an opening question to you around, you've just mentioned about next steps. What do you see as the sort of next phase of this that would be a practical bite-sized chunk that we could look at?
Thanks, Tony, it's a really good question. And it's honestly, so what I discussed earlier, it's largely around identifying those gaps and really it's ensuring that those gaps are finished. And this is tackling a bit more higher order level 8 testing and developing the methodology to handle that. It'll also be, I guess, in the intermediate, space, looking at some of those choreographed scenarios that we were unable to test on site due to site practicality reasons. So that would be an immediate point of call, but then also discussing potential avenues of testing some of the more complex, more dynamic cases with multi-vehicle interactions in a safe manner. That's really where I see this potentially transversing forward.
So certainly one of the things that the monitors talked to you about was the potential maybe if one of the users is actually commissioning a system on site and allowing the team to integrate with that process and look to see how that process would integrate at a live mine site. So I think there's a couple of opportunities potentially coming up with that, but if people are interested in that, they might let us know. So Eve, are we seeing anything on the chat?
Not at the moment, Tony, but I'm just wondering whether there is an issue online where nothing is appearing. So I'm just going to ask the participants if they could put their hand up if they do have a question to put to Dustin or yourself. And we have no questions.
Philip Henry. Craig.
Oh,
Craig.
Craig.
I think Philip got in first. No, Philip got in first.
Okay, Philip, please.
Philip.
Okay. Hey, hi. What speeds were the mid, the slow, and the high speed actually being tested? Roundabout. I mean, like roughly.
Yeah, that's a good question. So there's two parts to this answer. So because of our site, we limited that to what we could do safely. So it was around, I think, 5 being the lowest, mid being around 10, and then max being around 15 kilometers to 20 kilometers per hour that we could safely do with a haul truck and a light vehicle interaction. I've designated, and this is part 2, I've designated them as low, mid, and high in the hopes that it's generalizable to multiple sites. So really, it's not indicating that it has to be these speeds because that speed could be different. There could be different standards that are followed in different countries. So the idea being that we at least test a low-level speed or a high-level speed and a mid-level speed.
And in cases where there are two vehicles coming, that is a differential speed. So the high speed is then both vehicles are driving, let's say, 10 kilometers per hour, or is it actually both are driving 20?
That's a good question as well. So one of the examples I showed actually had both of them driving at the same high speed case. So that would be both at around 20 or 15 kilometers per hour. And then there was some variance tests that were conducted where we had one driving at the mid speed and the other driving at the high speed. So we always stuck to designating them as the low, mid, and high. So we always tested those specific speeds. But we did do some variance testing as well.
Thank you.
No worries.
So Craig, you are next. Thank you, Philip.
Yeah, Dyson, just some questions. Did you conduct detection, accuracy, and variance tests?
That's a good question, Craig. So we didn't go into too much details in really looking at specific accuracy of the detection. It was largely focusing on what the user saw in terms of an alert. So that was what was considered. However, the data that we gathered essentially can be used for that analysis as well. And it wasn't really conducted because of the scope of this current phase of work, but the fact that we've captured this information can still be compounded on with more tests conducted in the future. So we could potentially understand that. We've got GPS positioning of all the vehicles for all the tests. We've got LiDAR information to capture some of the ground truth information of those distances and positions as well.
Okay, what about an isolated vehicle detection test? Typical mine site scenario, like vehicles isolated, whether the system detected that as part of your tests?
Is that where essentially the haul truck is static and we have either a maintenance vehicle approaching, that sort of scenario, Craig?
Yeah, when either the haul truck or the light vehicle is electrically isolated in terms of testing
Yes.
with the PDS is still beaconing. Yep.
Yes, so that was essentially part of that test 3 choreograph scenario. So we had the haul truck completely cold start, so it was fully isolated, and then boots up to the to the PDS turning on, and then actually determining what that detection time was and where it was detected, that orientation around the local object.
Okay, thanks, Jason.
No worries.
Thanks, Craig. Peter's got his hand up.
Yeah. First, I had to figure out how to do that. I've never used put your hand up in this thing before. I don't know, but the question, or more just a discussion point, is, yeah, I agree with you guys talking about, testing scenarios is the next step, because one thing I think is difficult with the current approach is, say, for example, you had a vehicle circling another parked vehicle, and there's no real definition of what's a good result. There's just lots of data to look at, and as an end user, I'm not sure how you would decide which one is better. So, for example, the fact that the parked vehicle wasn't getting many alarms is entirely because it's parked, and so it shouldn't be getting alarms. It's nothing to do with detection capability, actually. It's because of the logic has said, well, this vehicle's in a safe state, so there's no reason to alarm. And that's where I think scenario testing is probably essential to actually do that interaction, because as the systems get more sophisticated, the context of what's going on is much more important. I think sensors like GPS are quite reliable at this point in time, so it's less about their accuracy and more about how intelligently can you decide what to do with that information. And then parked static situations don't count very much, because the logic would suggest there's no reason to alarm. But yeah, it's good work. But I think, yeah, scenarios is the next big thing to look at, of what the expected outcome is. So, and then you can decide what's a good result and what's a bad result.
Mm-hmm. Yeah, Peter, I think that's a really good question, and honestly a really good answer. It's largely, I think this component it is a very hard thing to quantify, because ultimately if you want to try and sell a system like this to an end user, they want to understand what that capability is, and I guess capability doesn't really say yes or no, right? So yes, having testing scenarios at least gives an understanding of what this particular system does in that scenario. And then ultimately it's up to the user to go, okay, that's what we want, or maybe can we change how this behaves in this scenario? Because we have had instances that, we want to try and avoid here. So that's the kind of discussion that could come out of some of this capability, at least at a baseline testing, is where I foresee it. But I do agree. I think capturing more scenarios and understanding them, and then really having essentially a way to look up and understand, okay, this is what the scenario should be doing, is something that we could do. Yeah.
And as long as the scenarios are well aligned with what the operators actually do, what are common situations that happen every day, then that'll have relevance to the end user who's trying to buy a system. So, that scenario happens on my site, so the results for that scenario are important to me, and I'll pay attention to them. Whereas some other scenario might be irrelevant to them. Well, they're probably not. But yeah, the PR5A scenario is probably a good start.
Thanks, Peter. Just to Craig's earlier point, as a user, ultimately there's some sensing stuff going on and some processing and everything. But as a user, I'm interested in latency. So, when is this thing detected, and how long does it take to actually get the right signal to the operator? So that to Craig's point earlier about capturing that information, the methodology should help you capture it. Now, what's good or not good can be determined by the physics and the speed of the vehicle in a given scenario as to the outcome. But
and that's what
latency needs to be a big piece of that, yes or no, in terms of is it meeting its objective? Because it can give you the signal, but it's too bloody late.
That's what makes it so hard to test, because latency and speed all are very important factors, and it's much more dangerous to test when things are moving around. It's nice to test stationary things. It's a lot easier to control. But yeah, it's for collision systems. That's a hard one.
So thanks for that chat, Peter. Look, there's 39 people on the call. Surely there's more people with a few thoughts or comments. This is don't feel afraid in this forum. It's a good open forum, and it's about collaborating and sharing and helping us improve. So please put your hand up if you've got any thoughts. a positive or negative. If you think we're going the wrong direction, happy to hear that as well. It's not about blindly just heading off into the yonder for this stuff. Okay, we've got Martin.
Hi, Tony. So I think this is great. This is a very nice scientific way to measure everyone's performance for a surface mine. I'm wondering if some of this can be applied in the future, and if you have planned to do similar methodology for underground testing. Yeah,
okay. Well, actually, the scope of this one was surface, as you say, but there is, under ACARP, there has been a series of projects running in the underground space. It was done at a more very specific scenario level. It wasn't as overarching in terms of the methodology. So we've had the underground team working with this team to look at whether there's a combination of approaches. And so far, the monitor's view is that the overarching piece of the methodology is the same. Obviously, the scenarios vary with the underground equipment. So it is our intent to bring forward potentially a document that covers underground and surface. A little bit more work to do, but yeah, it's certainly in the scope. Thanks, Martin.
Thanks, Tony.
So who's on this call that I'm going to call out?
I see Neil is there, Matt's there.
Yeah, no, I'm just... So, Phil Nelthorpe. Hello, Phil.
Good day, Tony. I was waiting for that.
So Phil is actually on the ISO committee that's publishing the 21815 standard. I think maybe you've got some insights, Phil, as to the challenges that lay ahead in terms of trying to get a common approach through an ISO standard. We've certainly learned some things about when the protocol went through, but anyway, over to you.
Yeah, so firstly, I think it's really good work. I think when I sort of read through about half of it last night, and I must admit I didn't appreciate the complexity of trying to get accurate data in this sort of surface mining scenario compared to a number of the tests that I've already seen done in the underground space, which is obviously slightly simpler in many ways. So it was good to see how it was done and the complexity of it. In terms of trying to get it into a standard, I think one of the significant issues will be developing pass-fail criteria. I would imagine the committee will want to have something to that effect, deciding what is an acceptable false positive, false negative type thing, once the test procedure is in place. And as Desmond mentioned, making sure that it is able to be undertaken in multiple countries by multiple test authorities. So I can see a fair bit of work going into trying to get a little bit more detail. But I guess also it's probably important, maybe Jason can comment on this, as to whether you could use different automation software for your data recording, or different computers and sensors, or whether it has to be that specific type that you've used at the moment, bearing in mind that things will change in sort of 5 years' time, which is probably when the standard is more likely to be available. So that's sort of a question back.
Yeah, no worries. I think I can say definitively that we try to ensure that it has longevity, I suppose. So it was developed, I guess the only factor is it's developed on Linux-based computing. So we should potentially have that into the future. There shouldn't change too much, but would it be one of those things where we could, I guess, generalize it, and then the main automation and the way the data acquisition system is really developed is up to whoever undertakes it?
Yeah, that's how I think the standard would have to put it. It would, can't be, you'd run into competition issues if you tried to spell out specific systems, I would think, but if it can be put in a more general sense as to how you would set it up without specifying hardware, software, then certainly a lot of what you've done is really good. And I think could certainly be very helpful to the committee in trying to get some sort of a test protocol together. The issue of what is pass and what is fail is certainly a far more complex one, I suspect. it will take a bit of thought. But even just to have the test methodology in the standard would help a lot for people wanting to develop systems and get them tested, and for the end users to be able to see some consistent results that they could compare from one system to another and one country to another. That's really good work.
Thanks, Phil.
Thanks, Phil. I see that we've got our friends from the United States on, the NIOSH crew. Jacob, I see you're on the call. I know that you guys have got some work happening in this space in your research world. Where does this fit in with that program, or complement it, or be interested in understanding where you guys are at?
Yes, Jacob, absolutely. It's of interest, and I think fits well with what we're doing. We've actually got a project on PDS validation, which John Homer is leading. I believe John is on the call. If you'd like to say anything, John.
Yeah, we're investigating within our project the methods and parameters associated with proximity validation for surface haul trucks. So this certainly fits that project that's our primary interest for attending the call.
Okay, so I think given that you guys are doing some work in this work, it might be a good idea for us to get our heads together. If we're going to put something towards ISO, then it's probably a collaborated approach that adds a lot more weight and hopefully speeds things up. Is that something that you guys would be open to?
Certainly, yeah, I agree with that.
Yeah, okay. Well, we'll take that one down as an action. I mean, we've had EMESRT has had a lot of interaction with the NIOSH, and I know you join the monthly calls, a number of you do. So we'll look to more formalise that after this session. We've got Patrice with a hand up.
Yes, this is fantastic work. And I'm Patrice from UTRAX. I'd like to continue in the same thought of my friend Martin and Phil on the testing side. So I believe that you said that the setup was about 2 days, maybe 9 hours of tests. But how much would you evaluate the setup of the data acquisition portion of the tests?
That's a great question. I think, admittedly, we didn't consider that in this because it was more of understanding what type of data acquisition system at a minimum point is required. So we tried to keep it simplistic in that if you can have basic computers, kind of embedded systems that you can implement onto each of these trucks and vehicles, it could be done. But we didn't quantify that, so that's something we could potentially look at. And I guess that's an area of interest that could be developed further. And the data acquisition system really is just a small, small component, I suppose, of the full methodology. But just to clarify, yes, that 2-day frame is actually purely for actually conducting those tests and running those repeats, running that randomization, doing tests 1, 2, and all the choreograph scenarios that we could get done on site as well. And then the data analysis itself takes a bit of time after that.
Any further questions, Patrice?
Yeah, sorry, I was muted there. Is there any thought put into place to maybe productize the data acquisition portion of it?
From our end, not really. We wanted to ensure that it's kind of generalizable to, including those open source kind of libraries that anyone could essentially develop and use themselves. It could be something that could be looked at into future, but that wasn't, I guess, the focus.
Okay. Thank you so much.
No worries. Thank you.
Thank you, Patrice. So who else am I going to pick on in this group? So Steve Clifton, I see you on the call. You've spent a lot of time in this space as well. What are your thoughts?
Hi, Tony. Morning, everyone. Yeah, it was a very interesting presentation. I'm keen to look at the results. I haven't looked at the results yet. But I do think, the more eyes you have, it's a very difficult thing to measure. As you say, we've done a fair bit of it ourselves, Tony, and the important thing is the repetition of scenarios exactly the same way to get a proper result and a proper judgment, and that's always difficult. I find anyway, in my experience, because you have constant learnings, and then your learnings sort of inform your next step to a degree sometimes. So that could be a challenge, I think, you know, to optimize and find exactly the best gauge for these systems. I don't know if you had any of that on this test. I'd be curious to know that as you went, you thought, oh, shucks, we should have done a bit of this or a bit of that at the same time. Did that happen?
Dustin?
Sorry, I was muted. Yeah, certainly we attempted this in you know, validating this methodology. So a lot of it was, okay, let's attempt this sort of testing and see what we can, but also maintain that generalizable outcome, so anyone can effectively run the same type of tests and the same type of scenarios. But that's also kind of a proponent, I guess, of the gap analysis, and something we could delve into further, really, as we go forward, especially if we start to target specific scenarios. And I think, like what you were saying, because we don't have a definitive yes/no answer or a pass-fail criteria for some of these cases, we could kind of build, if you will, a database of understanding throughout the years of these are the typical scenarios. Okay, they're performed in this way, and then the industry's flagged this is how this scenario should be performed, and that could be our benchmark.
Yeah, so run it sort of as a learning exercise that you sort of augment and grow.
Yes, yeah, exactly.
As you test, yeah. That's a nice presentation, thanks.
Thanks,
Thank you.
Steve.
Yeah.
Scott Montgomery, I see you're on the call. Any thoughts?
Yeah, great, Johnny. Yeah, great presentation, I have to say. You know, we look at it from a manufacturing point, where we look at all the different sensors that are being used and trying to integrate that to the OEM systems. To you know, so I'm really looking forward to see your next steps into how you take that forward and to control the vehicles, and just seeing what your thoughts are to progress there.
Thanks, man. We've got a bit of thinking to do after today. We've got a second time zone session on this afternoon to replicate this, to try and get as many people as we can. Well, look, unless anyone's got any other comments or questions they'd like to raise, is probably we allowed an hour and a half, but Dustin did a wonderful job getting through the content. Oh, Jamie, you've got a hand up.
Hello, good evening for people here in Europe, and good morning for you guys. First of all, thank you for this great work. I have as a last question of this part for you, Tony. If you guys have planned to keep making this like a fourth phase to include the analysis about how the collision avoidance or the PDS detect voids, or if you guys want to include different equipment as shovels, or if you guys want to test another collision avoidance with level 9, how it interact over the equipment. Because, you know, now the technology provider like my company, we are developing so fast collision avoidance systems, and we are willing to carry out many tests that we want to share with you guys in a near future. I don't know if this is in your roadmap, or if you will discuss it in another moment.
I think with the roadmap's unfolding, I think a comment was made a minute ago about you start to learn things along the way. We deliberately bit off this piece to begin with, because there were thoughts in the beginning around level 9 and whatnot, and it became clear to the monitors that if we tried to do everything, we would achieve nothing. And even now, it's taken us 3 years, and we ended up having to come back with some more money. So the original project funding was about $300,000. We came back with another 90. So as everyone knows, it's not a cheap exercise. So keeping your scope structured and milestone driven is a good thing. In terms of forming up those next milestones, that work is to be done, and I think these sessions were going to help us inform that discussion about the scope and what the potential next steps look like. So you know, if I get from your comments there, there's some quite specific things that you guys might be building or manufacturing, but the scope of this project is to operate at that more general level and not get into the specifics. So I think that we leave the specifics to the marketplace, because this could grow exponentially in terms of the effort. And by no means is this meant to become a certification type body either. That's up to others. That's more regional, jurisdictional things, or standards driven, as Phil mentioned earlier. So I think we've got to think very carefully through the next steps. But this working group is on our mailing list, and is consulted widely on a regular basis. So if as part of those potential next steps, it may well be we run a webinar and face-to-face workshop as part of that. We've yet to determine. So thank you for the prompt.
Thank you.
So, any further ones that we can squeeze out of anybody? So, I was going to close, but Matt Clements, are you still on the line, or did you lose us again? He's been dropping in and out.
Yeah, he has lost internet.
He's having some trouble.
Yeah. So,
okay. Well, look, I'll probably do the close and thank Dustin for his wonderful presentation and the team at Mining 3 for working with us on that. Eve for her always tremendous coordination and keeping on top of things. And Eve had the pleasure of being, she previously worked with Mining 3 and actually was part of the testing team, running around with high-vis vests on and hats during that testing. She had a ball. Yeah, everyone's quite invested in this process. So, look, thank you very much for your participation. Good discussion and some good questions. And by no means, the message for me out of today was we're heading in the right direction, but there's more work to do.
Yeah.
So,
Tony, before we finish, I just wanted to mention that we go back to our regular monthly reoccurring meetings at 8 o'clock and 4 o'clock, respectively, on Thursday, 3rd of June, just so that everyone knows. And then this afternoon session, of course, is on as well. I am recording both sessions, and then I'll be putting it up on the EMESRT website, and on the front page you'll get a little note as well to say that the webinars are there.
And for those who are not familiar with the monthly call, what we try and do is update you on things related to vehicle interaction. So it's not just this testing methodology, that's one of the topics, but it's the ICMM Cleaner Safer Vehicles initiative that's got the VI component. There's other things happening in the research space. So in general, that half-hour call is about keeping you, connected and collaborated about what's happening and letting you know what's coming up. So if you haven't been joining that call, if you want to keep up to speed on things, then I'd encourage you to join us on a monthly basis. And sometimes it only runs for 20 minutes. It depends on what's happening. So, but look, unless anyone's got any further comments, thank you for your time today. So there's no hands up that I'm seeing. So
no.
I think we'll close it out and have a great day, everyone.
Yes. Thank you, everybody.
Thanks, everyone.
Thank you. Thanks all.
Bye. Thank you.
Thanks, Scott.
Thank you. Bye.
Thank you. Bye.
Thank you.